Good morning, my dear students. Today's lecture I am talking about completely randomized design, which is also known as CRD. The topic is designed for the B.Sc 6th semester major students and C.B.C.S 4th semester generic students under Dibrugarh University. After completion of this lecture, you will be able to know the basic characteristics of a CRD and the basic layout of CRD, the model used in this design, the assumptions used in this model, the merits and demerits of the design, the interpretation from the ANOVA table. This is the introduction part of this design. Completely randomized design, which is also known as CRD, is the most simplest of all other design. Here the principle of randomization and replication are used. In this design, principle of local control is not used. The design is suitable for only the experimental material is homogeneous. Here the treatments are allocated at random to the experimental units and the number of replications may vary from treatment to treatment. This is the treatment allocation procedure of CRD design. The whole experimental area is divided into a number of experimental units, say capital N. See, here the whole experimental area is divided into n units. Suppose we have p treatments. We have to allocate these p treatments according to their replications. First, a random selection of n1 experimental units is made and one of the treatments is applied to these units. Next, a random selection of n2 units being made from the remaining capital N minus small n1 experimental units, and any of the p minus 1 treatment is applied to this unit. The process is continued until all the treatments being replicated. This concept will be clear from the following example. See this example. Suppose we have three treatments N, P and K respectively. Here N replicate 3 times. The treatment P replicates 4 times and the treatment K replicates 5 times. So the total experimental area is divided into 3 plus 4 plus 5 equal to 12 equal parts. So see, at first the whole experimental area is divided into 12 equal parts. So first we have to replicate N in this experimental unit. Here see, N replicate 3 times. So we can allocate N any 3 units out of these 12 equal parts. So first we allocate N here, and next N is allocated here and here. So now we have 12 minus 3, that is 9 parts. So we have to allocate treatment P out of these 9 equal parts. So the treatment P is replicated 4 times. So the treatment P allocated here, here, here and here. So we have only 5 equal parts. So the treatment K is allocated remaining 5 plots. Here the fixed effect linear model is Yij is equal to mu plus alpha I plus epsilon ij, where mu represents the general mean effect and alpha I represents the effect due to the eye treatment and epsilon ij represents the error effect. Here the assumption is that summation of Ni alpha I over summation I is equal to 0 and the errors that is denoted by epsilon ij's are independently and identically distributed as normal with mean mu and variance sigma square. The ANOVA table is here the source of variations are treatment, error and total variation. So degrees of freedom is we have P treatment. So the degrees of freedom due to treatment is P minus 1 and we have total n units. So the degrees of freedom for total is n minus 1 and for error degrees of freedom we have subtract the treatment degrees of freedom from the total degrees of freedom. Here, the third column represents the sum of squares. Here, capital HD square represents the sum of square due to treatment and capital S square represents the sum of square due to error and capital S square represents the sum of square due to total sum of square. And the main sum of squares are obtained dividing the sum of square by respective their degrees of freedom. So, the treatment mean square is obtained by dividing the treatment sum of square by their respective degrees of freedom P minus 1 and error mean sum of square is obtained by error sum of square divided by degrees of freedom. Next, we have to calculate the F statistics. F statistics is calculated dividing the mean sum of square due to treatment by error mean sum of square and this is the F statistics. Now the conclusion from this ANOVA table is that if the calculated value of Ft is less than the table value of F for P minus 1, n minus P degrees of freedom at certain level of significance, you may take 5% or 1%, then we may accept our null hypothesis at that particular level of significance and may conclude that there is no significant difference between the treatments. And otherwise, we may reject the null hypothesis and conclusions are drawn accordingly. Here, we have discussed some merits of CRD. So first is that its layout is very easy. And the next is that there is complete flexibility in this design. That means any number of treatments and replicates for each treatment can be taken. In this design, whole experimental material can be utilized. The next advantage is that the analysis of the data is simplest as compared to any other design. Here, missing observations create no problem in analysis of the data. The design has some demerits also. So, the design is suitable for small number of treatments. It is difficult to find homogeneous experimental units in all respects. So, CRD is seldom suitable for field experiments as compared to other experimental designs. These are the references for this lecture and thank you for watching this video. Thank you.